All right. I'd like to know how was your study by the online course on section 1.9, 1 and 2.2. How was your study? Is everything all right? So, if I assume everything's all right, then I'd like to invite someone to participate to study our course. So the aim is to remove stones. You can remove one, two, three, and the goal is to win the game. If you can win the game with me, then you will get one extra point. Okay, so let's take parents. We can remove the stone one, two, or three. And the game is who take the less stone will win the game. Or so now tell me what happened if I go first. You want to, okay, so you need to go first. Okay. When you take the stone, you just give a cross. So means the stone is taken. Okay. Tell me your reason why you took stones.
Because the remaining stone is 20, and we can take 1 to 3 stone. Then we can set the stone into 4 in a group. Then we will have 5 groups. And if you take any, if you do any operation, I will take 4 minus your operation stone. Then I will take all the left stone, and I will win.
Okay, good. Thank you. You can do that. One extra point. Okay, so actually, he's calculating the total number of stones himself. And I draw this box. Okay, so if you know the total number, then you can follow the rules. When we prove this problems by backtracking. All right. So let me rephrase this question again, and I'd like to invite another one to let you win the one extra point. So let me change the rule again. If we can take one, two, three, four stones and take in turns, how do we do this game? Anyone? You want to try it again? Five minus my number. Very good. So maybe you can follow these rules if you know these questions. Okay. If you study the online course, you will see how we prove you always win if you go first. So that's why I like to play this game with my nephews. So if they win me, then I give them red emerald. So they can try many times, but I won't give them any red emerald. Okay, so that's one problem of section 1.9. So next, let's see chapter 2. So point 1, we have learned the definition of set. Okay, so maybe I can go to one interesting problem of Russell's paradox. Okay, so let me remind you of the related paradox. So when we use the keyword paradox, that means we have contradiction for every case of this problem. For example, if Harry is the father who shapes all people who do not shape themselves, okay, then we can ask this Harry shape himself. Okay, so let me give you one example. I shape my head myself, so I don't spend any money in the barber shop. Okay, so I'm the person who shape myself. In this case, Henry will not shape the head for me because Henry always shapes people who do not shape themselves. Okay, so do you understand this assumption? Okay, so now we can ask the question: Does Henry shape himself? Okay, so let's assume if Henry shaped himself, then what kind of contradiction we have? Because Henry always shapes people who do not shape themselves. So if they shape themselves, then it's a contradiction by assumption. Okay, then what happens when Henry do not shape himself? Okay, so shape will shape people who do not shape themselves. So he will shape himself. It's also a contradiction. So you can see by either case, if Henry shows himself or do not shape himself, we all have the results of contradiction. That's the reason we call this a paradox. Okay, now I want you to write down the Chinese sentence of why for the set, if S is a set of all sets which are not members of themselves, then we can get the paradox S is a member of itself. Okay, so we call this Russell's paradox. I want you to write down two cases why the set problem is a paradox. I'd like to invite one student who explain the paradox in Chinese for everyone. Anyone? 好，那用中文帮大家解释一下，这个谬论是什么？语法师谬论。这个语法师，然后他会帮所有不帮自己语法的人语法。那这个不同的是，亨利会不会帮自己语法？因为如果假设亨利会自己语法的话，那他会违反他提倡所有不自己语法的人语法的这个原则。那如果他不帮自己的话，那因为他要帮所有不帮自己语法的人语法，所以这个事情跟整件事情是有悖的。And now apply this concept to the original Russell's paradox. How to explain this problem? S is a set of all sets which are not members of themselves. Why S is a member of itself is a paradox. Alright, so you can see for either case we have contradictions for the problem if X is member of itself. So we call this Russell's paradox. One extra point, remember go to TA after class. Alright, then we see a lot of definitions for that. Okay, then we have our homework 3. So I just updated the date to to one more. Okay, so because the question of these three sections is relatively less than the other sections, we have only three questions for each section. So I hope you can take this assignment next week. Is this okay? All right. All right, then section 2.2 set operations. I believe you have learned this before: intersection, complementation, symmetric. Okay, and today we're going to introduce section 2.3. Okay, it's functions. In this section, we will see definitions of a function, what is domain, codomain, image pre-image, and we will see different types of function: injection, suggestion, bijection, and also other type of functions: inverse function, composition function, graphing functions, and floor ceiling, very particular, very special functions, factorial functions. And then we will see what is partial function. All right, so based on this definition of set, then we can further define what is a function. If we have two non-empty sets A and B, then we can define the assignment from the element from A to B. So we use the definition F, which map the element from A to the set B. Then we can write f of A equals B as a function, which tells us the assignment of each element of A is exactly one element of B. So if you can assign or map the element of A to one element of B, then we can write f of A equals B. Okay, so basically, you can see the definition of functions. Actually, it's built upon the definition of set. Once we have two non-empty sets A and B, then we can define how elements are assigned from A to B. Okay, so we also call this mappings or transformations. So you will see these keywords a lot when we have researches in computational field or AI field, because actually when we apply AI models to predict the results from input, actually we are considering it's a function because we have input data A, and then we have the predicted result B, and we consider the AI model is a function. Okay, and we can map the input to output. So actually we have very broad meaning of functions. Now let me ask you one question from the definition of function. If we have the assignment of each element of A to exactly one element of B, can we have empty elements that has no assignment of the set B? For example, we have C, D, F. There is no assignment from element A in the set A to the element C, D, F. Because this is now in the definition of function. It's again, right? Because it only tells we have the assignment for each element of A to exactly one element of B. Okay, so if there's no mapping from element A to element B, for example, C, F, then this is okay. It's still function. Okay, so next, can we have one element in the set A which is not mapped to any element in B? For example, we have 1, 2, 3, 4. And I have another element 5 here. In the 5, we have no assignment from this element to any element to the element C. But the set B. This is allowed for the definition of function? No, right? Because let's see this definition again. We need to have an assignment of each element of A to exactly one element of B. Okay, so you need to assign the assignment for every element but we have this special case in the end of this section. How we have the empty elements in the set A. So we have another definition of this called partial function. Partial function is now empty elements of A as wrong assignment to A element of set B. Alright, so maybe we can consider function as a relation because we define how these two sets, how to map elements by these two sets. So you can also see the notation like cross or a multiplication, or we call this relation. So let's see the definition of a relation. The subset is restricted to be a relation where no two elements of the relation have the same first element. Okay, so we call f of A equals B. A is the first element. So no two elements of the relation have the same first element. That means, okay, so you can see in this case, we have multiple elements mapping to the same element of B, right? And we also have one element mapped to another element. Okay, so the definition of relations, it tells us no two elements of the relations have the same first elements. Then we call that a relation. Then we can rewrite the definition of relation to propositional function or practical logic. For all x is a, then we have exists some y in the set B, and x, y in the relation f. Okay, that means we need to have one assignment from A to B for all elements. And then we have another condition for all x, y1, and y2. If xy1 and xy2 y1 equals y2, which means no two elements in this relation have the first elements. Okay. So actually, you can rewrite all definitions in this textbook by the propositional function by yourself. So maybe after we introduce the first sections, you are capable of writing all this unit sentence to propositional logic. All right, next let's see more definitions. Once we have the function for these two sets x and y, then we set f is the mapping from x to y, and we call x is the domain of f, y is the codomain of f. Okay, remember we have two sets, x to y or a to b. So the first set we call that domain, and the second set is called codomain. And then if we mapping the element A to B, then we call B is the image of A under F, and A is the pre-image of B. Okay, so you can see actually image and pre-image is defined for individual element, and domain and codomain is defined for the whole set. Okay, and then we can have another definition of range of F, which is the set of all images of point X denoted by F of X. So that's where it maps, we can call the range. Because we already know we need to map every element in A to some element of B. But we may have some elements of the set B which is not mapped by the element of A. Okay, so actually we can implement the range. How many elements is mapped by A? So we have yellow region, which we call range, or image of the function. Alright, next, the definition of equal function. Two functions are equal when they have the same domain, the same codomain, the domain to the codomain to the same element. Okay, so this is a very strict rule. You need to have the same domain, codomain, and the assignment of the elements must be all the same. Then we can call this equal function. Okay, I want to write down one example of two functions which are equal. Just give any example you can think of. They are two equal functions. So you need to make sure the function f or two set. The domain and codomain are the same for these two functions. And then for each assignment, it's the same under the function f. Then we can call that equal functions. Alright, what kind of equal function you are writing? Say that again. X plus 1 squared. Okay, so let me write down his functions. Okay, f of x equals x plus 1 squared minus 1 minus 4. And g of x equals x squared plus 2x minus 3. Right? Okay, so actually we have the domain for codomain. So we have the domain for real numbers and codomain for real numbers. Okay, actually you can just define for real numbers, that's okay. And then we have the same domain codomain for f of x and g of x. And then let's see we have, whether we have exactly the same assignment for every element. So actually you can verify x plus 1 squared plus 4 is equal to x squared plus 2x minus 3. So we have exactly the same assignment for every real numbers within our set. All right. Next, let's see how we represent functions. Okay, previously we have seen formula. Okay, you can just define a mathematical formula to mapping x to y. But we have other different ways to assign or representing functions. For example, we have students and grades. Okay, so everyone sitting in this classroom will have your midterm examination scores or final examination scores. Okay, so you can see actually also function. And then we can have computer programs. Once you have input into your program and you your program after the calculation, it will have some output. It may be also the assignment or implementation of functions. All right, next, a very quick exercise of this function. What is f of a? Okay, so you can see it maps to the element of z in the set B. Okay, and image of D. Okay, so we can see D is mapped to Z. Okay, and then the domain of F. Then we have the set A. Okay, and codomain of F, the set B, and pre-image of Y. Y is mapped from B, right? Okay, so the pre-image of Y is B. And you can also write pre-image of D by the definition of set because we have multiple elements mapped to Z. So you can write the set ACD. Okay, very simple exercise. And then we can combine the definition of set to functions. If we have F under the set A to B, and S is the subset of A, then you can use the subset S as the input into the function. Then our output will also a set, and we collect all elements F of S under the property if S is the element of the subset F of S. So in this case, once we have ABCD set A, then our subset is ABC, and F of the subset ABC, and we can see A mapped to B mapped to Y, CD also mapped to C. So in the end, we could have a set of F of 1C as a result in F of CD. Let's see the definition of injection function because we have seen the legal mappings of the function. We can have one element assigned to one element or multiple elements assigned to one element. So the first type of function is injection. So function f is set to 1 to 1 or injective function. You can only give f of a equals f of b by that a equals b. Okay, so you can see f of a, that means the assignment or the mapping from a to another element in the set B equals the element B in the set A. Okay, they map to the same element, but in that condition, A equals B. Okay, so we have the function 1 to 1. A equal to Z, E equal to Y, C equal to X, E equal to W. We don't have multiple assignment from AB to Y, for example. Because by definition, if A assigned to Y, then A must equal D. So we call this 1-to-1 function. Next, the second function is the function from A to B. You can only give every element B in the set B. There is an element A in the set A, that f of A equals B. Okay, so you can see we need to extend every element in the set B. There should be one element in the set A mapped to that element. So we call this onto or surjective function. Okay, then by the previous two definitions, we have one-to-one correspondence. It's both surjective and injective. So you can see the mapping is 1 to 1 and onto. Every element in the set B is mapped by the element from the set A. Okay, so next you will see a lot of different questions to ask you to prove if the function is 1 to 1 or onto. Okay, So let's see the rules, how we prove such. Okay, let's see, to show that F is injection. Okay, so you need to show that for arbitrary x and y, f of x equals f of y, then x equals y. That's proved by the definition of injection. Okay, now if you need to show that f is not injective, okay, so you can find a particular element x, y in the set A, and f of x equals f of y. That means we have multiple elements mapped to the same elements of the set B. Then this is not injective function. Okay, so write down the name of the type of the proof of study in the section 1.9. What type of proof of this? So we have learned different strategies how to complete the proof, right? Okay, so what's the name of this proof? We have the strategies that use proof by different cases, and we have proof of existence, right? And we have the proof to prove unique existences. And we also have the strategies of fact or reasoning. Okay, so what type of proof of this? How about you? Anyone? And for the proof of injection, you need to show that arbitrary xy that follows this condition. Then once we need to prove not injective, we just need to find a particular elements of x and y. Then if f of x is equal to y, then it's proved. What this type of proof is called? Okay. Okay, I'll say that again. That's right, very good. Counter example. Okay. Because every element follows that properties. If you can find a counter example, particular element is y, that does not follow these properties, then just one counter example, so we can prove that it is not injective. One extra point. Okay, next to show that as a subjective, we can just follow the definition directly. Consider arbitrary element y, and f of x equals y. You can always find one element mapped to arbitrary elements. Alright, so what kind of rules of inference of this? You can just consider one arbitrary element of y, then you can find one element from A mapped to that element. And we can conclude this is a subjective function. Write down the name of rules of inference. What is this called? All right, what's your answer? Say that again. Uh, Existential generation. Okay, no, it's not. Anyone? Okay, so this is universal generalization. You can pick arbitrary element x. If that's true, you can assert for all x, p of x is true. So in this case, we just pick arbitrary element y from P in box that definition, and we can assert for all elements within y and P, and the property holds. So this is what we call universal generalization. Right? So you need to remember this closely because we use it everywhere in discrete mathematics. Alright, the last one to show that F is not surjective five particular elements, and we have no assignment from set A to that element. It's also a counter example. So remember this because we will see a lot of different questions to ask you to prove if a function is 1, 1, 2, or projection. All right. So next, let's see very simple steps to show that f is 1, or on 2. So if f is a function from the set ABC to the set 1, 2, 3 by f of a equals 3, f of b equals 2, f of c equals 1, f of d equals 3. So is f an on2 function? So remember the definition of on2, we need to have every element in the set B, which is mapped by n elements from A. So if we have ABC mapped to 1 to 3, then 3 is mapped by A, 2 is mapped by B, and 1 is mapped by C. Okay, so then we can conclude all elements in the set B is mapped by some elements in set A. So f is 1 on 2 function. Okay, next is the function f of x equals x squared. From the set of integers to the set of integers on 2. Okay, so you can see if the set from integer to integer, then we have positive integer, negative integer, and 0. Okay, so if f of x equals x squared, that means all the elements from A map to positive integers of the set B. So we have a lot of elements which is negative integers. That is not mapped by the element. So this function is not on 2. Right, next let's see a new definition, inverse function. If f is bijection from A to B, then the inverse f we can identify. And this function is from the set B to A. So you can see the order is reversed. Originally we have the function from A to B. Now we have the function from B to A. So that's one we call that inverse function. So f inverse y equals x, we can only give f of x is y. So we have 4 orders, and we normally consider the inverse functions. And we have y back to x. Right? Then let's see. The inverse function is defined by bijection functions. That means we need the function f to be 1, 1 and on 2. Then we will have inverse function. So let's see why we need to define by bijection function. Let's consider if this is not 1, 1, what happens? If it is not 1, 1, that means we have multiple elements mapped to the same elements. So when we consider the inverse of y, we have only 1 to multiple elements. So that does not follow the definition of the function. So for the second case, if it is not on 2, that means we have some elements which has no assignment from the element of the set A. So when you consider f inverse y, then you cannot discover any mapping results. Okay, so that's the reason a we need to find the inverse function based on a bijection function. All right, so the visualization is very easy. Once we have f from a to b, for example, the inverse function will be y back a and w. All right, so let's see this example. If we have f defined from abc equal to 3, and we have f of a equals 2, f of b equals 3, and c equals 1. If this function is invertible, then what's the inverse function? Okay, so we have 3 elements in A, 3 elements in B. So let's examine this bijection function. It is right? 1, 1, and 2. So we can find the inverse function. So we can write f inverse 1 is C, f inverse of 2 is A, and f inverse of 3 is B. So this is our inverse function. Right? So if we have a function f from z to z, and f of x equals x plus 1, then you can also examine it is if it is 1, 1 and 2. Actually, if you map x to x to 1, so that definitely 1, 1 and 2 for all elements in z. So in inverse, we will write f inverse of y equals y minus 1. So if you map 2 to 3, 3 to 4, then when we map it back, 3 will map to 2, 4 will map to 3. Alright, maybe you can try this by yourself. Let's see some spatial functions, floor and ceiling. Okay, so if we have the element x is floor operations, we are trying to discover the largest integer which is listed on the equation x. For example, 3.5, the largest elements integers is equal to 3.5. Okay, and for the ceiling, we need to discover the smallest integer which is greater or equal to x. So the smallest integer which is close to 3.5 is 4. So that's the definition of floor and ceiling functions. Alright, next let's see composition function. So if we have function from B to C and G is A to B, actually we can compose of F with G. Okay, because if G at A to B, then we can apply F to that B to C in the next step. So we can compose both functions. So we call that compositional function or composition of F with G. So you can write a elliptical between F and G to indicate a composition function. Okay, so by the definition, we apply G of x first and then F of G of x. Okay, so you need to remember the definition. Once we have the first given, F composes G, and then we need to calculate G of x first and then F of G of x. Okay, and then you can see actually when we apply G of x, we have A to B, then we use element B as the input of the function f. So we can transform the element B to element C. Alright, this is the visualization of composition functions. Once we can transform A to B to C under the function G and F, then we can just omit the middle parts because the compositional function F with G just went from step A to step C. x squared and g of x is 2x plus 1, then the composition f with g, remember we apply g of x first. Okay, so g of x, actually we are mapping x to 2x plus 1. Then 2x plus 1 is used as input to the function f. So for this one, this variable, now it is 2x plus 1. Then when we have the square, it becomes 2x plus 1 squared. Okay, similarly, you can also apply the composition g with f. Anyone has different results. Alright, so let's see the composition example. If we have g from set ABC to itself, g of A equals B, g of B equals C, and g of C equals A. And we have another function f, which map ABC to 1, 2, 3, under the function f of A equals 3, g of B equals 2, and C equals 1. And what is the composition f with g? Okay, so now we can examine if f with g, that means we need to map the element from g is ABC to ABC, and f is ABC to 1, 2, 3. So if we calculate g of x first, we calculate the set. When it is used as input for f, it maps to ABC to 1, 2, 3. Alright, so when we verify it is okay, and we can write the composition function f with g of A. Okay, so remember the g of A is B, and f of B is 2. Okay, so f with g of x equals 2. And then you can follow for all elements within the domain. Okay, next let's see the graph of functions. Actually, we can define all pairs, especially older pairs, from the set A to B under the function f. Then, when we collect all these older pairs into the set, then we can draw the position of the graph. For example, we have element A in the set A, and f of A equals B. Then we collect older pair AB into the set. So once you can collect all elements in the set A, then you will have a lot of number of order pairs. Then we can draw the position of the 2D graph. For example, if f of A is 2n plus 1, then the domain is n to n. Okay, then you can try n from 0, 1, 2, 3, 4. Okay, so when a is 0, the output is 1. When a is 1, the output is 3. So you have the order pair 0, 1 as our first pair, and 1, 3 as our second pair. Then you can follow 1, 2, 3, 4 by yourself, and you can draw the graph of this function. And you can also draw the function of floor or ceilings. Okay, so that looks like this. Next, let's see some properties of floor and ceiling functions. Okay, so take 1a for example. If the floor of x is n, that means even only if x is within the range, x is larger or equal to n, and x is smaller than n plus 1. Okay, so maybe we can try some examples. If x is 3.5, then the floor of 3.5 is 3. So you can see actually 3.5 is greater or equal to 3 and smaller than 4. That's it, right? Because if x is 3 point something, then after the floor operation, we will get 3. If it cannot be 4, if it is 4, then the floor of x is not n. Okay, so you can verify this by yourself. Next, let's see how we prove the properties of floor and fitting functions. Let's see this example. If we want to prove that x is real numbers, then the floor of 2x equals the floor of x plus the floor of x plus 1 by 2. Okay, so let's see the trick, how we prove the properties of floor and fitting functions. So the difficulty is we don't know the results of x plus 1 divided by 2 by the floor operation. Because if x plus 0.5 and x is a real number, so if the decimal part is greater than 0.5, then it will change to another integer. But if x is, for example, 3.2 or 3.3, the decimal part is less than 1 divided by 2, then the results will be 3. Okay, so you can see x is 3 point something, then the results could be 4 or 3. So in that case, we need to have different case to show that different results. Okay, so in this case, we define x is n plus epsilon. N is the equal part, epsilon is the decimal part. So if x is 3.5, then n is 3, epsilon is 0.5. So we separate the equal part and decimal part. Then we have two different cases. The first case is epsilon is less than 1 by 2. Because we already see we have x plus 1 by 2. So we need to consider if it is over 1 or less than 1. So first case, if epsilon is less than 1 divided by 2, then we can see this number plus 1 divided by 2 is not over 1. So we can determine what's the value of floor of x plus 1 divided by 2. So let's see how we prove both sides are equal. Okay, so firstly, let's see left hand side, we have 2x's. So remember, x is epsilon, so 2x is 2n plus 2 epsilon. And we know 2n, this is integer, right? So the floor of 2n is 2n. How about 2 epsilon? If epsilon is less than 0.5, then 2 epsilon will not over 1. Right? For example, epsilon is 0.3, then 2 epsilon will 0.6. So it's still less than 1. Alright, so you can see the floor operation of 2x and 2n because this one is 1. So this is the left hand side, that's the right hand side. Okay, for the right hand side, we have x plus 1 by 2. So we already see this is the most difficult part. But now we know epsilon is less than 1 divided by 2. Okay, so if x is epsilon plus n, so now we have n plus epsilon plus 0.5. Okay, so we can see this is the integral part, this is the decimal part. If epsilon is less than 0.5, then these two numbers, still less than 1. So we can conclude the result of floor operation is only n. Alright, next we have only one term, x, the floor of x. So we know x is n plus epsilon, which is the floor operation. Epsilon is less than 1 by 2. So the result is 0 n. Now we have the left hand side, we have 2n. In the right hand side, the first term is n, the second term is also n. So we have 2n equals 2n. So we prove the first case. Okay, so I hope you can try the second case by yourself. What happens when epsilon is larger than 1 divided by 2? Okay, you can see for this part, if x is n plus epsilon, then plus 1 divided by 2. Epsilon plus 1 divided by 2 is larger than 1. Okay, so we have a trick here. Okay, we can use 2 epsilon minus 1 make this decimal part within the range 0 to 1. Okay, because we are fully confident that 2 epsilon is already over 1. So I hope you can try other process, the steps by yourself. Okay, next is the factorial function. Okay, so let's see if we have two different sets n to z plus, okay, by the function f of n equals the factorial n. So actually we are trying to map the natural number n to 1 times 2 times n minus 1 times n. So that's a factorial function. So if you try f of 1 to f of 20, then you can see we have very, very large numbers by this factorial function when n equals 20. Okay, the last thing is partial function. So let's see the definition of partial function. It's from the set x to y. Okay, but if it is a partial function, then we can write x prime to y, where x prime is the subset of x. Okay, so now you can see you don't have to use all elements in x. Once you can get the definition of partial function, then the partial function can define the subset of x. Okay, so we write the partial function by this special notation to indicate it's a partial function. Okay, of course, if our subset is the original set, then we call this a total function. So previously, our definition of function, they are all total functions. But here we have a special definition of partial functions. Okay, let's see this example. If we have n mapped to real number r, and f of n is the square root of n, so which is a partial function from z to r. Okay, so you can see the domain is non-negative integers because we need to calculate the square root of n. Okay, so actually we are using non-negative integers as our input. And then it can map to real numbers. So this is one example of partial function. All right, we have 3 minutes left, so I hope you can combine all this concept of different functions to solve this problem. If we have the function defined from real number to real number, and f of x is the 4 of 3x minus 1, and g of x is x divided by 3, then what is the inverse function of the composition function x plus g of the number 2? Okay, so you can see actually we are using a set of notation. This is a set contains only element of 2. Okay, so what is the inverse function of this composition function? All right, please write down your answer on the paper. When you finish your answer, you can raise your hand. If your answer is correct, I will give you 1 extra point. I think goes first. Okay, please write down your answer here. Alright, thank you. Alright, so let's see its answer. If we need to discover the inverse function of this composition function, we need to know what is the composition function first. Okay, so the composition f with g of x, actually we can see we apply g of x first, and then use as an input to f of x. So g of x is x divided by 3. If this is the input to the function of f, then we have 3 times x divided by 3 with the floor operation divided by 1. So that gives us x with the floor minus 1. Okay, so that will be the composition function. Then we need to discover the inverse function of this composition function. Okay, so we need to determine if we have this composition function, what maps to the element 2. Okay, so now we have x with the floor minus 1. If this is mapped by 2, okay, then we know x with the floor operation equals 3. Then what is x? Okay, so you can see x could be 3.1, 3.5, 3.9, and 3, right? So actually we can write x is within the range 3, x larger or equal to 3 and less than 4. Okay, so this answer is so good because we need to write into the form of set because we are trying to map a set of element 2. Okay, so we need to write the answer of x in R by the property 3 less than or equal to x less than 4. Okay, so you can see this is also a set that maps to that set. Okay, one extra point. Any question today? Okay, if no questions, then we stop here.上课有没有讲到，就是你们的影片里面那个东西？我知道，其实是他们要期盼会变好，了解，再跟助教讲。陈伟，同学说我们那个影片呢、在1.8的章节没有包含到棋盘格的这些图片。你们1.8后来，我们上次上课大概是上到这边，从这边就没有上了这样。 对，所以
上面没有上完。
从76就没有上了，但是同学说好像那个我们给的影片里面这些地方都没有这样。你们再确认一下好了。
OK。
好。
这是哪一个？
好，1.8。1.8我们上次上到74页，所以要有75页之后的影片这样。好，谢谢。